Okay, welcome to video number 15 of the Diaries of a Coronavirologist YouTube channel. Today is the 15th of April, 16th of April even, and we're up to about 2.1 million cases confirmed of COVID-19 around the world and about 143,000 deaths. So tonight's topic is going to be vaccines. I think I may end up doing a few different videos talking about vaccines in different ways. Because vaccines are a brilliant way to deal with viral disease. They work. Vaccines save lives. Vaccines don't cause autism. Just get that out at the front end. So what I want to do tonight is do a fairly general intro to vaccines, and I'll probably talk a little bit about the first vaccine approach that went into trials in a bit more detail, and then in future videos I may talk about some of the other approaches that are being used. So the main aim of any vaccine strategy is to safely train the body to rapidly detect any invading virus. So the way this is done is by putting in some part of a virus or an inactivated virus or an attenuated virus such that the body will mount an immune response against something that won't cause the same disease as the full-blown virus would. So classically, let's take polio, for example. There were two approaches used, which were attenuated virus, a live attenuated virus, which is the oral polio vaccine, or the inactivated polio vaccine. So for inactivation, the virus is chemically treated such that it's destroyed and it can no longer infect cells and replicate. But the immune system can still detect it and can still mount an antibody response to it. With the attenuated vaccine, this was made in the lab by passaging the virus. So passaging can be on cells. You can grow the virus in cells in the lab over and over and over, or in monkeys at different temperatures. Various different things can be done. But ultimately, this means the virus adapts to growing in those conditions such that when you put it into a human, it's not as equipped to grow and cause disease. So again, the body can detect that virus that you put in, even though it's not going to replicate very well and it's not going to cause disease. The immune system can still see it, and it can mount an antibody response. That then generates immunological memory, such that when the real virus is encountered, the immune system's ready to go quicker. It knows the antibodies it needs to produce, and it produces them rapidly and can therefore protect against infection. So it all comes down to for the body being able to detect the virus. And the main thing that gets detected when mounting an immune response are the external parts of the virus. So if you think of all the pictures going around of coronaviruses, it's always the ball with the spikes coming out of it. And as I've talked about in previous videos, that protein that sticks out is actually called spike. So with coronaviruses and vaccination to SARS2 coronavirus, the aim is to train the body to detect spike in a safe way. If the virus infects, your immune system is going to be able to detect spike, but you're going to get disease in the process. So vaccines are trying to train your body to see spike, but not get disease. As I say, I'll probably do multiple videos about vaccines and all the different strategies that are going to be tried. The WHO currently has a list of about 60 different approaches that are being tried. Also, 60 different candidates with various different approaches, just to specify. But tonight I just want to focus on one of these, which was the first one to go into clinical trials in humans in Seattle in March. So this was the most rapidly developed vaccine that's ever gone into humans. The genetic sequence, the RNA or DNA sequence for SARS coronavirus 2 was published on the 11th of January after the virus was identified and determined to be a coronavirus on about the 7th of January. 2 months later or so, on the 16th of March, a vaccine was ready to start going into humans in Seattle in this phase 1 trial. So this vaccine was produced in a collaboration between the NIAID, so the National Institute of Allergy and Infectious Disease here in the United States, and a company called Moderna, and it's an RNA vaccine. So Moderna has RNA in, and they focus on making mRNA vaccines. So the idea behind an RNA vaccine is that you can trick the cells of the human body into producing the proteins that are going to be the target of an immune response without having the virus present. So the way a virus works is that it carries, in the case of coronaviruses, RNA. It puts that into a cell. The cell doesn't realize that it's not its own RNA, and it just reads that RNA sequence, which is the instructions, or which are the instructions to produce proteins. That then produces all the proteins the virus needs to make more copies of itself. One of those proteins is obviously spike. So the vaccine candidate that's being produced by Moderna uses the RNA sequence for spike, but none of the other viral proteins. So when that gets injected into the body, I believe the trial is injecting into the arm, the RNA can go into cells, and it will have the instructions to tell those cells to make the spike protein. Those cells will make the spike protein, but none of the other virus proteins, so no infectious virus is being made, just the spike protein. The immune response can tell that that newly produced protein is something foreign, and it can do its immune response thing and start to produce antibodies to the spike protein that looks like a virus. So in principle, you're triggering the same kind of immune response you would get if the real virus were present by targeting spike. So it all sounds simple enough when said like that. We're essentially doing what a virus does, putting RNA into cells and making those cells produce a protein that the immune response can detect. But it's only that one protein, so there's no disease. However, RNA vaccines, have never been found to be effective in humans. No RNA vaccine has ever worked. So whether this is going to work, we don't know. Love to think it would, but at this stage it's too early to tell. And right now we're just in the phase 1 trial. So this phase 1 trial is taking about 100 people and having a control group that don't receive any vaccination or receive a sham vaccination, and then 3 different groups that receive 3 different levels of mRNA, so 3 different dose groups. And it's looking to determine whether the vaccine is safe, so see if there's any adverse reactions to it. Classically, there might be some soreness at the site of injection. There might be a bit of a fever or these kind of things. So looking to see if any of that develops. And then looking to see if the people that receive the vaccine actually produce antibodies that are effective. So taking blood samples, getting the antibodies, and seeing if those antibodies can react against the SARS2 coronavirus. So this all takes time. It takes time for the body to mount an immune response. It takes time to check that that immune response is effective. But if it's found that it's a safe vaccine approach and antibodies are being produced that are capable of inhibiting the virus, then we can move into a phase 2 and eventually phase 3 trial where we start to study more and more people and start to look if this vaccine really works. But again, all of that's going to take time. In a lab setting, it's fairly easy to work out if a vaccine is protecting from the virus because you can actually directly give the virus to the study animals. So let's take monkeys, for example. You can inject a monkey with the RNA vaccine. You can let the immune response ramp up, and then go down, as would kind of happen in a human. And then you can infect those monkeys with the virus and see if the vaccine is protecting against infection. Ethically speaking, you can't give humans this virus. You can't directly give it to them to see if the vaccine is protecting them from it, because if it's not, then that's a bad situation to be in. So instead, what you need to do is set up a study where you vaccinate a certain number of people, and then you compare those people to people who haven't received the vaccine to see if there is a lower level of infection in your vaccine cohort. But that takes time because you need people to be getting infected. So you need your control group and potentially your vaccine group to be exposed to the virus out in the world, but that's taking time. Lots of people still haven't been infected with SARS2. So this is why we're talking about the fact that vaccines may take a year to 18 months to 2 years to be widely available, because we just need that length of time to check that they are working. We don't want to spend a lot of money and time and effort into mass producing a vaccine and giving it to everyone and then find out that it wasn't protective at all and that we've just wasted all of that effort. Now, the other reason to take time and to properly assess everything is that we really need vaccines to be safe. They're designed to save lives, and when they work, they do save lives, but they need to be safe. They can have negative effects. And I'm sure everyone is aware of the fake science that has led to the anti-vaccination movement. So if we rush a vaccine here and it turns out that it caused some negative effects, then a huge amount of trust gets lost and vaccines become harder to implement because there's a bigger anti-vaccine movement. And vaccines really are the best way we can combat viral disease. So this is why it's going to take time to have a vaccine available. But I am optimistic we will get one within that 18 months to 2 years, maybe within a year if we're really lucky, kind of time frame. So that's all I want to say for tonight. I could probably spend a lot longer talking about all the different types of vaccine approaches that are being used and how the antibodies are inhibiting infection in more detail, but I'll save that for other videos. Tonight, I just wanted to give you the idea of what a vaccine is trying to do in terms of training the immune system to detect the virus, and that's largely through the detection of spike, and talk specifically about the Moderna vaccine that was the first one to go into clinical trials, and that it's an mRNA vaccine and how that works. And I also wanted to explain why it's going to take such a long time for us, seemingly such a long time for us to get a vaccine, this year to 2 year kind of time frame. And that really does boil down to the fact that we need a lot of time to make sure this works, make sure it's safe, and that it's going to save lives, because vaccines do save lives. So thank you for watching. As always, please keep subscribing and sharing and dropping likes on these videos if you're enjoying them, and please keep leaving comments and feedback and asking questions. As I say, I will try and get to them as time allows. Sorry if I'm a bit slow. And as always, please stay safe, wash your hands, and keep calm and carry on. We will get through this pandemic eventually when we have a vaccine, for sure.